Okay, so in this video, we are going to see something known as linear power flow or linear load flow or distribution system. Linear load flow. Okay, so load flow, what is the load flow? Basically, we are solving the steady state equations of the system. Uh, System means it can be a transmission system or a distribution system. So what are the components present in the system? We have basically two categories of components. One is the network. Network consists of the lines, transmission lines or distribution lines. The other component is generator and loads. So the equation that describes the network part and the equations that describe the generator and load component, those are so how does they look like? So for network, we represent the bus currents, basically bus injections, and the bus voltages. They are related by these simple linear equations, which is y bus into v bus. So this is a matrix linear equation that represents the network part in the system. Okay, this is a linear equation, linear in terms of current and voltages. But where is the non-linearity coming in picture? So non-linearity is coming because of generator and load component. So the bus current injected at different buses, that is related to bus voltage vector by some non-linear functions, right? For example, suppose we have at a particular bus a constant power load connected, so that S and V is the voltage. Then what is the current taken by that load? It is basically S divided by V conjugate. Now the relation between current and voltage is, you can see it is a non-linear because voltage is coming in the denominator. So that's why this is a non-linear equation. So this is for constant power model. Similarly, we can go for other type of model like constant current or constant impedance, where we have the terms of V square and all coming in picture. So there we have a non-linearity. So there is the non-linearity. So when we are solving load flow equation, we are essentially solving this non-linear equation. F of V bus is equal to Y bus into V bus. Right. And since there are several thousands of buses present in the system, so we have a set of equations, nonlinear equations, which need to be solved simultaneously. And there is no closed loop analytical solution that can be obtained for such a thousand number of nonlinear equations. So what we do is we take some initial assumption on the unknown parameter. So in this case, unknown is a bus voltages, so we initialize all the bus voltages at say 1 per unit and solve the equations iteratively in iterative fashion. And then we have how to solve them. So we have several methods like Gauss-Seidel or Newton-Raphson in transmission, or in distribution we have seen the backward forward sweep or direct load flow or Gauss implicit Z bus. So all these methods are there. And those methods provide, after the end of iteration, they provide a very accurate solution. The accuracy can be controlled by the help of tolerance that we set. So we define the tolerance, say 10 to the power minus 6. That means we are telling the algorithm that give me the solution which is accurate up to 6 decimal places. Right. So algorithm will take some time, perform several iterations, maybe 10 iteration, 12 iteration, 15 iteration, whatever, every time. And it will give the most accurate solution as per the accuracy we demand. That is fine. But most of the times, when it comes to real-time operation, and the system size is very large, and we need to perform several number of load flow cases. For example, one of the application is a state estimation, or we have seen the application of time series load flow and probabilistic load flow. So in those applications, we need to run the load flow several thousand number of times. So for large system, it will take time when we demand a very accurate solution. And suppose we are running the state estimation or optimal power flow. So this is required for real-time operation. So suppose our scheduling interval is say 5 minutes or 15 minutes. So in that short duration, and we are asking the algorithm to give very accurate solution, then it will take a lot of time. It may not converge within the 5 minutes for a practical large number of bus systems. So in that case, what we do, we take approximation that we assume the non-linearity component to be not there, we linearize those equations and solve that equation as a linear equation. So when the equation becomes linear, we don't need several iterations. We can solve it in just one simple iteration. So we reduce a lot of computational burden. But what is the cost of that? We are approximating. We are neglecting the nonlinearity components. So and most of the times, even the approximate solution is also working because we have the system operator has to take some decision which may be based upon the approximate results. We did not go for a very high accurate solution. So at that point, we need this linear load flow. So what we are doing basically, we are linearizing that equation and solving ultimately that equation as a linear equation, right? So in case of transmission system, you may be familiar with something known as DC load flow. So DC load flow is basically what we are doing. We are treating the AC circuit, and we are AC circuit as a very approximately a DC circuit. Okay, so what we are writing the power flowing between bus say I and J. We are approximating is as the angular difference between theta I and theta J, bus number I and J, and divided by the reactance that connects between between those lines. So it is similar to a DC circuit equation. So, and we solve these equations simultaneously, and we solve for something known as DC load flow. And this is again approximate linear load flow for valid for transmission system. So this is for transmission system. So what are the assumptions here? We are neglecting the non-linearity component. So sine theta is approximated as theta. The resistances of the line are neglected. The voltages of the lines, voltages at the buses, we are treating that approximately equal to the nominal voltages. So that is the one per unit. So under a lot of assumptions, we are formulating the problem like this. So can we apply DC load flow, which is again a linear load flow? Can we apply that as it is to the distribution system? The answer is no, because distribution system has particular characteristic that their resistance is not negligible. The angular difference is very small, so the power flow is not related to angular difference only, it related to voltage amplitude also. So here we need to have some other formulation. So we need to take a different set of assumptions here and perform the linear load flow. Okay, so the DC load flow is there is only one single iteration. We are not solving it iteratively, right? The same thing we want to achieve for the distribution system. So let us see how to go ahead with the linear load flow for distribution systems. Okay. So now the problem, let us discuss the basic working principle of that linear load flow for distribution system. So basic formulation. So here we have the nonlinear equation. The nonlinear function of the bus voltages is equal to y bus multiplied by v bus. So the objective here is to solve for bus voltages, which is an unknown quantity, right? So let us assume that the bus voltage can be expressed as a nominal voltage V naught minus the deviation from nominal voltage that is represented as delta V bus. I have put a minus sign there because in distribution system at all the buses except the substation, the voltage is decreasing because there are passive loads connected and since the radial distribution systems are mostly radial in nature, so voltage keeps on decreasing as we go away from the substation. So there is a voltage drop. So that minus sign is there. Okay, so now the nonlinear this f of v bus, that nonlinear function that can be written as the nonlinear function of v naught minus delta v bus. And here objective is to linearize this equation. So we can apply Taylor series. So when we apply Taylor series, that can be written as f of v naught minus f dash v naught. So f dash represents the first order derivative of the function f, with respect to V and evaluated at nominal voltage. So that is the meaning of F dash V naught. Multiply by delta V bus plus we have some higher order terms. Okay, we have the higher order terms. And since we are interested in formulating the linear load flow, so we neglect higher order terms, we treat them as negligible. So under which condition we can neglect that? When we neglect it, when the delta V bus, that is the deviation from nominal value, is negligible. That is the delta V bus is negligible. So this is valid when the system is under nominal operating conditions. But when the system is under transient conditions, such as a fault scenario, or when we are studying the extreme stressed conditions, such as voltage stability boundary. So under that conditions, the linear load flow is not valid. So only under nominal operating conditions, the linear load flow assumption is valid. Okay, so that is the important point. Okay, let us further simplify that. So we have neglected higher order term. So this is f of v naught minus f dash v naught. The delta v bus that can be written from this expression as again v naught minus v bus. Okay, so that can be written as f of v naught minus f dash v naught multiplied by v naught. So what I will do, I will just group this term, then plus f dash of v naught multiplied by v bus. Right. So you can notice here this term, it is only dependent upon the V naught, and V naught is just a number. It is just a nominal voltage. For example, a 33 kV system, it is just a number equal to 33 kV. 11 kV system, it is just a number which is a constant term. So this circle term is a constant term that can be treated as a some C, and this term again, it is also another constant. We can treat it as another constant n. So now we represented that function, which is a nonlinear function f of v bus as m times v bus plus c. So this is we converted it into a linear equation that is equal to y bus v bus that we have seen already. So here, just a simple rearrangement of terms. Let us take V bus on one side and C on the other side. So what we can write from here, let me make some space here. Okay, so basically C is equal to Y bus minus M times V bus, right? And here the unknown quantity, only unknown quantity is a V bus. So that can be solved as Y bus minus M inverse multiplied by C. Right. So this is the way we approximate by neglecting higher order term or neglecting the non-linearity, and we obtain the V bus, which is approximate solution in just a single iteration. We no need to perform iterations again and again. So this is the basic principle of operation of linear load flow. Now let us see how to formulate it for our system. Okay, so let us take the example of a general distribution system. Here we have bus number one as a substation, and the system can be radial in nature, or there can be some branches emerging out of some buses, or there can be loop formations. Does not matter. So here we have, we can write the bus injections, which are basically the current injected at respective buses. So I1 represents the substation bus injection, followed by I2, I3, and I2, I3, and so on up to, let us say there are n number of buses. So this vector is basically represented as I bus, and that is related to the bus voltage vector. The bus voltage is vector is basically V1, V2, and so on up to Vn. So this is V bus, and it is this will be Y bus matrix. So in Y bus we have Y11, Y12, and so on. Y1n, then we have Y21, Y22, and so on, Y2n, and so on here. So n number of buses. Okay, like that. Now, notice that here we are interested only in obtaining the bus voltages of all the buses except the substation bus, because substation is what system operator has control over, that can be maintained at a particular value, and we don't know other bus voltages. So we are interested in obtaining this circled part of the voltages, right? So we are not interested in obtaining the substation bus. So we can just partition the matrix in these two components like this, the substation component and the component other than the substation. So we can just partition these matrices like as shown like this. Okay. So here the partition thing can be written as like I1 and I capital N, where I capital E N includes the bus injection starting from bus number 2 to N, that is equal to Y11, which is essentially this component. Then we have Y1N, which is essentially that row vector. Then we have Yn1, which is essentially this vector here, that is Yn1. This is Y1N, and finally Yn. So Yn is basically this partition, that is Yn. And here we have substation voltage and V capital N, which we are solving, which we want to solve for. Fine. So this is the thing. So this is the network equation, which is already linear in nature. We are not interested in this linear component. I mean, we are not making any approximation here. This is the exact linear formulation. Now let us see how to model the nonlinear load component. So let us take any bus, say bus number K, kth bus, and some load is connected S, K. The load has different components. It is represented as a ZIP model. So it has a constant power component, constant current component, and constant impedance component. And how we need to formulate, we need to see how much current is taken by that kth load. Let us assume that Vk is the kth bus voltage and Ik is the current taken by that voltage. Now here we need to obtain the relation between Ik and Vk. So that equation will be a nonlinear equation. Let us see that equation. So let us assume that we have a ZIP model of the load. So yeah. So when we formulate ZIP model, then we need to see when voltage is nominal. So nominal voltage is basically V naught, and when voltage is different than the nominal. So let us denote as V. And here we have three different components. First is constant power. So here I will write this constant term. So let us discuss constant power term first. So the constant power term is not dependent on the voltage. So when nominal voltage is there, let us say SP is the corresponding apparent power. And when I am writing SP, it is basically a complex quantity. So it has a real part as well as imaginary part. So when I'm saying constant power, I mean constant real power as well as constant reactive power. So treat it as a complex function. So when voltage is V, when voltage changes, the power still remains the same. So it is SP only. Okay. Now let us consider constant current component. So when voltage is nominal, let us say SI is the SI is the power. But when voltage changes, what happens? When voltage changes, then remember that the thing is that the current remains constant. Okay, so current remains constant. So what is the equation of current? So SI divided by V remains constant is equal to constant. What is this SI divided by V? This is basically current conjugate. Okay. So suppose SI0 is the nominal power when we have nominal voltage, and SI is the power when voltage is V, then this quantity is also equal to SI0 divided by V0. Okay. So this gives what is the corresponding power? What is the SI? We need to obtain the equation for SI. So that is basically SI0 multiplied by V by V0. Okay, just by simple rearrangement, you can obtain that. Fine. So I am deriving here the equation in terms of complex number. So remember that when I am writing V by V0, the V is a complex number. It has both magnitude and angle. V0 is also a complex quantity. It has magnitude and angle. Okay, now let us discuss constant impedance part. So let us assume that when voltage is nominal, this is SZ0, and here impedance is remaining constant. So impedance is remaining constant means Z remains constant, which is represented as mod V square by SZ. Okay, so that is equal to mod V naught square by SZ0. So it is basically this one. So impedance is given by mod V square by S conjugate, and I am writing the equation for which impedance remains constant. Okay. So what does that give? What does that give? Basically, we need to derive here the equation for S shade. So here conjugate cancels each other, and this is basically S shade 0 multiplied by mod V square divided by mod V naught square. So that is the equation we can obtain. So what is the conclusion ultimately? When we have ZIP, all three components present in the system, then the total load at that kth bus that can be represented like this. So here we have SP at kth bus. So I am writing it with suffix k. Okay. Then plus we have SI suffix k. So that k represents SI0 at suffix k into V by V0. So here V again Vk. And this is SZ0 at kth bus. And this is mod V a square divided by mod V0 square. So that is the load power. Now what is the load current IK? It is basically, sorry. Okay, so we are supposed to find IK. It is given by SK conjugate divided by VK conjugate. So let me substitute for SK conjugate. That is, so we have constant power component plus constant current component plus constant impedance component. And its conjugate. Okay, so I just substituted a ZIP model, and let us simplify that. So this is 1 by vk star. This is, so since it is a conjugate, so let us do the conjugate. So this is spk plus spk conjugate, then si0k conjugate. This is vk conjugate divided by v0 conjugate plus z0k conjugate. This is just absolute value, so this is vk square divided by v naught square. So conjugate we did, and let us multiply by vk conjugate in the inside. This is spk conjugate by vk conjugate plus i0k conjugate divided by v0 conjugate. Remember that here vk conjugate gets cancelled, plus z0k conjugate divided by mod naught square, and here denominator is vk conjugate and the numerator is vk square. Okay, so that quantity can be represented as vk into vk conjugate. So this is just by a simple linear algebra, complex algebra rule. So this can be represented like this, because any complex number square is basically a into a conjugate. So here we can cancel out this term and that term. So ultimately, this is the equation. Okay, so that is the equation part. Okay, that is good. And let us see where is the non-linearity coming in picture. So we are looking at non-linearity between ik and vk. So the first term here, the vk conjugate is coming in the denominator. So there is a non-linearity term. This term, second term, is a constant term because it is dependent on the given uh, load power of the constant current part and V naught. So these are just numbers. It is independent of voltage, independent of current. So there is no current or voltage term. So this is a constant term. And the third term is linearly dependent on the Vk. So the only nonlinear term is this corresponding to constant power component. So we need to now linearize that term, and let us see how to linearize that. Okay, so let us just see how to linearize this one by any complex number, one by v. Okay. Okay, so let us see how to linearize a complex quantity which is represented as 1 by v. So we need to linearize it. Okay. So as we have seen, that can be represented as v naught minus del v, that we have seen already. And here, let us take the term v naught as a common term. So that becomes 1 minus delta v by v naught. And by Taylor series expansion, so Taylor series of 1 upon 1 minus x. What is that? That can be represented as 1 plus x square plus and so on till the infinity. So starting from here onwards, here we have higher order terms which can be neglected. So these can be neglected to 0. For x, absolute value of x within unit circle, within when these values are less than 1. So that is the Taylor series gives that. So what we can do is that 1 by v0 term is there, this term, and this we can represent it approximately as 1 plus delta v by v naught. So that can be represented like that. Okay, that's fine. So here we have represented 1 by v as 1 by v naught, 1 plus delta v by v naught. Now let us simplify again. So this is 1 by v naught 1 delta V. Again, what is the delta V? So from this equation, it is V naught minus V. So let us represent that. So this is V naught minus V divided by V naught. Okay, so this is, let us separate. So V naught by V naught is 1 minus V by V naught. Right, so this is V by V naught. So that term becomes 1 upon V naught 2 minus V divided by V naught. Okay, so this is the linearization we got. Right. So this is the linearization. Let us substitute that term here. So here we have VK conjugate, so that here the conjugate term will come. The rest of the thing is fine. Okay. So let us write IK is represented as SPK conjugate, and here we had 1 upon VK conjugate. So just to replace V by V conjugate here, then V conjugate there. That's it. Other things will remain as it is. So this becomes 1 by V naught by V naught, and what else? 2 minus VK star divided by V naught. Right. Plus we have the current component, which is given by S I0 K conjugate by V0 conjugate. Yeah. Then plus this term. Okay. So that is the thing. Let us rearrange the constant term together, the VK conjugate term together and VK term together. Okay. So what are the constant terms? It is basically S VK star by V naught 2. So basically this term plus S I0 K star by V naught conjugate. So these are just constant numbers. Then here we have minus S PK star by V naught square multiplied by VK star plus S Z0 K star by V naught square multiplied by VK equal to IK. And this IK, yeah. So this is the equation for kth bus current. Kth bus current for all K. K belonging to starting from bus number 2, 3, and so on up to the n number of buses. So this is the equation, and we can write this equation in the form of a matrix. So let us write that. So left hand side we have IK. So we can write this as I2, I3, and so on up to IN. So we are just writing all such equations, arranging them in a matrix format. Okay. The first term is some constant term. So we can simply put that in a constant matrix like this. So K instead of K, it will become the corresponding quantity. So of course K equal to 2, it will become 2, K equal to 3, it will become 3, and so on. So it is 2 SPK star divided by V naught minus, sorry, plus I0 K star by V naught star. Okay, so this is corresponding to bus number 2. Similarly, corresponding to bus number 3, we have to SP3 star by V naught plus S I0 3 star by V naught conjugate, and so on up to n number of buses. So here we have SPN. So this is for nth. So this is a constant matrix. Then going ahead, we have the second term, which is coefficient is Vk star. Okay, and for all k, this v0 square is a common term. So let me take minus 1 by v0 square outside. So that becomes minus 1 by v0 square, that term outside. And here is a matrix, and here is another matrix. Okay, so I'm writing the second term in a matrix format. So here is a Vk star. So Vk star is basically here we have V2 star, V3 star, and so on up to Vn star. Okay, so this is a n by 1 vector. Yeah, n minus 1 by vector. Now here the coefficient of Vk star is Spk star. So we can put corresponding terms in these matrices. So here we can write Sp2 star, and it is not dependent on V3, V4, and Vn. So we can put 0, 0 rest of the times. The next term is Sp3 star, which will appear in the diagonal position, and other terms will be 0. Similarly, this will become a diagonal matrix. So this is Spn star, and this is 0, 0, all 0, 0 terms. Okay. So this is a diagonal matrix. So just now we have represented the second term. Similarly, we can represent the third term in the form of a diagonal matrix because the pattern is similar. So here we can write plus 1 by v0 square, and that matrix can be represented as sp2 in the same matrix. Sorry, SZ. So this is SZ0 for 2, bus number 2 conjugate, then SZ0 for bus number 3 conjugate, and so on along the diagonal. So this is SZ0 for nth bus conjugate. So this is a diagonal matrix, and here we have V2, V3, and so on up to Vn. Okay. So I just wrote the equation in the matrix format, and what is this? This is basically a constant term, some constant term. Okay, so let me write this matrix as A. This quantity, this matrix as plus B times Vn conjugate. So notice that this is basically Vn conjugate. We just define the Vn vector as here. Yeah, here we have defined the Vn as consisting of V2, V3 up to Vn. Fine. Yeah, and plus let us define this quantity as C. So this will be C. So it is a, when I am writing C, it is a complex matrix, and this is similar same as Vn. And this is basically In. Okay, so let us take that equation on the next page. In equal to, so in equal to a plus b times vn conjugate plus c times vn. There's the equation. But what is the ion? Ion can also be represented in terms of fibers that we have seen here in the previous slides. So here from this ion, what is ion? Ion is basically y n1 v1 plus y n n vn. So let us represent that. So this is basically y n1 v1 plus y n n vn. Right. And since LHS is equal, we can equate RHS on both the sides. So here we have y n1 v1 plus y n vn is a plus b vn conjugate plus c vn. Okay. So let us take all the terms on right hand side. So left hand side will become 0 and a minus y n1 v1. I will combine this because this is a known constant term. Then here we have plus b vn conjugate plus c minus y n n vn. Okay. So this is the equation, and it is linear equation in terms of Vn. Our objective is to solve for Vn. Let us see how to solve for it. So all others, this A, V1, Yn1, B, C, these matrices are known matrices to us. So we can solve for it. So let us write 0 equal to, let us write this as A dash, let us write this as C dash. So that becomes A dash plus V Vn conjugate plus C dash Vn. And this is since this is a complex number, we can represent that in the form of a real and imaginary. So let us split that into real and imaginary. So on the right hand side, we had A dash plus B Vn conjugate plus C dash multiplied by Vn. So this is A dash real plus J A dash imaginary. So I am splitting it into real and imaginary plus this is B real plus J B imaginary. And here it is Vn real. And since it is conjugate, so the imaginary part will be minus Vn imaginary plus C dash real plus J C dash imaginary. And here we have Vn real plus J Vn imaginary. Okay, so I'm just splitting that. The right hand side is also, sorry, the left hand side is obviously 0. Okay, so let us simplify this further. So this is A real plus, sorry, A dash real plus J A dash imaginary plus, so this becomes BR VNR plus BI VNI plus J VI VNR minus BR VNI. So I just perform the matrix, sorry, complex operations plus C dash R VNR minus C dash I VNI plus J times C dash VNR plus C dash R VN Okay, so here we get a simplified form, and we need to separate the real part equation and imaginary part equation. Both are can be equated to zero. So 0 is equal to, let us write the real component first. So real part is basically AR dash plus BR. So let us, I will circle those components. So basically this component, this, and this. So here actually we can combine the terms which are coefficient of V and R, this and this. And I can simply write as BR plus C dash R multiplied by B and R plus VI, right, minus C dash I V and imaginary. So this is the real equation. And similarly, the imaginary equation can be written as, which is the coefficient of J, the remaining terms. So this is basically A dash I. And here also I can combine the terms which are and R, this term can be combined, and this Ni and Ni, this term can be combined. So that becomes like this. Vi plus C dash I multiplied by V and R, and right. So here we simplified the equations, and again let us write those equations in a matrix format. So what we can do here is the constant terms, we can take it on the right hand side, the AR dash and AI dash. So that becomes minus AR dash minus AI dash, that is equal to the coefficient of V and R and V and I that we need to write. So that becomes like this. So this is Vn real and Vn imaginary. So coefficient of V and R in first equation is BR plus CR dash. Coefficient of V and I is BI minus CI dash. Similarly, okay, so that is the equation, and the only unknown here is this term. So this is very similar to AX equal to B format, and as we saw in the previous lecture, we can solve this equation for X as A inverse B. Without doing the inverse of A matrix, we can solve it by means of LU decomposition and backward forward substitution. So here we can solve for real and imaginary values of the percentage. So that is the algorithm for our this linear load flow. Yeah. So in next video we will see some example. By means of example we can understand it.